To locate a reprint of the 1897 National Electrical Code, you can explore several avenues. Firstly, consider contacting the Electrical Trades Supply Association. They offer a reprint service for the 1897 NEC. You can reach them for details. Secondly, for online access, the Hathai Trust Digital Library provides a digital copy of the 1897 NEC in PDF format. Hugo Books offers a preview of the 1897 NEC, but it might not provide a complete copy. Thirdly, check with your local public library. They might have a copy or be able to access a digital version. Research libraries at universities may have collections of historical electrical codes, including the 1897 NEC. Furthermore, contact electrical industry organizations such as the National Electrical Contractors Association (NEC) or the International Association of Electrical Inspectors (IE) to inquire about access to historical codes. Visit antique or used bookstores that specialize in electrical or construction materials. They may stock old editions of the NEC. You can search for copies of the 1897 NEC on eBay, but be aware of the potential for forgeries. It is important to note that the 1897 edition of the NEC was not published by Underwriters Laboratories, all but by the National Board of Fire Underwriters, which is now known as FM Global. When examining electrical systems, grounding and bonding are critical for safety. Grounding ensures a low impedance path for fault currents, protecting equipment and people. Bonding connects metallic parts to create an electrically conductive path, minimizing voltage differences. Together, they help prevent electrical shock and fire hazards. Article 250.4 of the National Electrical Code addresses the requirements for grounding and bonding. The purpose of grounding is to limit voltage imposed by lightning, line surges, or unintentional contact with higher voltage lines, and to stabilize voltage to earth during normal operation. Active grounding creates a low impedance path for fault current to return to the source, which facilitates the operation of overcurrent protective devices. Bonding is the permanent joining of metallic parts to form an electrically conductive path that ensures electrical continuity and the capacity to conduct safely any fault current likely to be imposed. Proper bonding minimizes voltage differences between metallic parts, reducing the risk of electric shock. The code provides specific requirements for grounding electrodes, grounding conductors, bonding jumpers, and methods of bonding. The size and type of grounding and bonding conductors are determined by factors such as the size of the overcurrent protection device and the type of system. For example, Table 250.122 in the National Electrical Code provides guidance on sizing equipment grounding conductors for grounding raceway and equipment. Regular inspection and maintenance of grounding and bonding systems are essential to ensure their continued effectiveness. Corrosion, loose connections, and physical damage can compromise the integrity of these systems. When designing and installing electrical systems, it is important to consult the latest edition of the National Electrical Code and other applicable standards to ensure compliance with all grounding and bonding requirements. Understanding the principles and practices of grounding and bonding is crucial for electrical safety. Regarding conductor ampacity, this refers to the maximum current in amps that a conductor can carry continuously under specific conditions of use without exceeding its temperature rating. Several factors influence the ampacity of a conductor, including its size, insulation type, installation method, and ambient temperature. The National Electrical Code (NEC) provides tables and guidelines for determining conductor ampacity based on these factors. The NEC Table 310.16 is a key reference, offering ampacity values for insulated conductors rated up to 2000 volts, based on conductor size and insulation type, assuming an ambient temperature of 30 degrees Celsius, which is 86 degrees Fahrenheit, and no more than 3 current-carrying conductors in a raceway or cable. Correction factors are applied when the ambient temperature is higher than 30 degrees Celsius. For example, if the ambient temperature is 40 degrees Celsius, you would need to apply a correction factor from Table 310.16 to reduce the conductor's ampacity. Adjustment factors are used when there are more than 3 current-carrying conductors in a raceway or cable. These factors also reduce the conductor's ampacity to prevent overheating. For instance, if there are 4 to 6 current-carrying conductors, the ampacity must be adjusted to 80% of the value listed in Table 310.16. Conductor insulation types, such as THHN, THHW, and XHHW, have different temperature ratings. THHN, for example, is rated for 90 degrees Celsius in dry locations, while THHW is rated for 75 degrees Celsius in wet locations. Selecting the appropriate insulation type is crucial for ensuring the conductor can operate safely at its rated ampacity. Installation methods also affect conductor ampacity. Conductors installed in free air have a higher ampacity than those installed in conduits or cable trays. This is because conductors in free air can dissipate heat more effectively. When calculating conductor ampacity, it is essential to consider all relevant factors and apply the appropriate correction and adjustment factors. Overloading conductors can lead to overheating, insulation breakdown, and potentially fire hazards. The NEC provides guidelines for protecting conductors against overcurrent, such as using circuit breakers or fuses with appropriate amp ratings. Understanding and applying the principles of conductor ampacity is critical for electrical safety and ensuring the reliable operation of electrical systems. Now consider voltage drop, which is the decrease in voltage that occurs along a conductor due to its impedance and the current flowing through it. Excessive voltage drop can cause equipment to malfunction, reduce the brightness of lights, and decrease the efficiency of electrical systems. The National Electrical Code recommends limiting voltage drop to no more than 3% for branch circuits and 5% for feeders. Several factors influence voltage drop, including the conductor's length, size, material, and the current flowing through it. Longer conductors, smaller conductors, and higher currents result in greater voltage drop. Conductors made of materials with higher resistivity, such as aluminum, also experience more voltage drop than conductors made of copper. To calculate voltage drop, you can use Ohm's law, which states that voltage drop is equal to the current multiplied by the impedance of the conductor. However, for AC circuits, you also need to consider the conductor's reactance. The following formula is commonly used to calculate voltage drop in a single-phase AC circuit. Voltage drop equals 2 times the current times the length of the conductor times the impedance per unit length. For a 3-phase AC circuit, the formula is voltage drop equals the square root of 3 times the current times the length of the conductor times the impedance per unit length. To minimize voltage drop, you can increase the conductor size, shorten the conductor length, use conductors with low resistivity, or reduce the current flowing through the conductor. The NEC provides tables and guidelines for selecting conductor sizes based on the allowable voltage drop. When designing electrical systems, it is important to calculate voltage drop and select conductor sizes accordingly to ensure that equipment operates properly and efficiently. Overcoming excessive voltage drop is essential for maintaining reliable power delivery. Regarding short circuit current rating or SCCR, this is the maximum fault current that a component or assembly can safely withstand without causing a fire or electrical hazard. It is a critical parameter for ensuring the safety and reliability of electrical systems. The SCCR of a component or assembly is determined through testing and is typically marked on the equipment. The available fault current at a specific point in an electrical system is the maximum current that can flow during a short circuit. It depends on the utility supply capacity, transformer impedance, and the impedance of the conductors and other components in the system. The available fault current must be less than or equal to the SCCR of all components and assemblies in the system. If the available fault current exceeds the SCCR of a component, the component may fail during a short circuit, leading to a fire, explosion, or electrical shock. The National Electrical Code requires that all electrical equipment be selected and installed based on its SCCR and the available fault current. Section 110.9 of the NEC states that equipment intended to interrupt current at fault levels shall have an interrupting rating sufficient for the nominal circuit voltage and the current that is available at the line terminals of the equipment. Section 110.10 of the NEC states that the overcurrent protective devices, the total impedance, the component short circuit current ratings, and other characteristics of the circuit to be protected shall be selected and coordinated to permit the circuit protective devices used to clear fault currents without extensive damage to the electrical components of the circuit. To determine the available fault current at a specific point in an electrical system, you can perform a fault current study. This involves calculating the impedance of all components in a system and using these values to determine the maximum fault current that can flow. Several software programs are available to assist with fault current calculations. When selecting electrical equipment, it is important to verify its SCCR and ensure that it is adequate for the available fault current. If the SCCR is too low, you may need to use components with higher SCCRs or reduce the available fault current by adding impedance to the system. Coordination studies are performed to ensure that overcurrent protective devices such as circuit breakers and fuses are properly coordinated to minimize the impact of a short circuit. These studies involve analyzing the time current characteristics of the protective devices and selecting devices that will trip quickly enough to protect the equipment, but not so quickly that they cause nuisance tripping. Understanding and applying the principles of SCCR is essential for electrical safety and ensuring the reliable operation of electrical systems. When dealing with electrical panels, also known as panel boards or load centers, these are essential components in electrical distribution systems. They serve as a central point for distributing electricity to various circuits throughout a building. Electrical panels typically contain circuit breakers or fuses that protect each circuit from overcurrents, such as short circuits or overloads. The main components of an electrical panel include the enclosure, the bus bars, the circuit breakers or fuses, and the neutral and ground bars. The enclosure is the metal cabinet that houses all the components of the panel. It provides protection from physical damage and helps contain any electrical hazards. The bus bars are conductive bars that distribute electricity from the main incoming power supply to the individual circuits. They are typically made of copper or aluminum and are rated for a specific ampacity. Circuit breakers and fuses are overcurrent protective devices that interrupt the flow of electricity when a fault occurs. Circuit breakers can be reset after tripping, while fuses must be replaced. The neutral bar provides a connection point for the neutral conductors of the circuits, while the ground bar provides a connection point for the grounding conductors. The electrical panels are available in various sizes and configurations to accommodate different electrical loads and applications. The size of the panel is determined by the number of circuits it can accommodate and its ampacity rating. The ampacity rating of the panel should be sufficient to handle the total load of all the circuits connected to it. When installing electrical panels, it is important to follow all applicable codes and standards, such as the National Electrical Code. The panel should be located in a readily accessible location and should be properly grounded. All wiring connections should be made securely and properly identified. Regular inspection and maintenance of electrical panels are essential to ensure their safe and reliable operation. This includes checking for loose connections, corrosion, and damaged components. Over time, circuit breakers can weaken and may need to be replaced. Understanding the components and operation of electrical panels is crucial for electrical safety and ensuring the proper distribution of electricity in buildings. Now, consider transformers, which are essential components in electrical power systems that transfer electrical energy from one circuit to another at the same frequency but usually with different voltage levels. They operate based on the principle of electromagnetic induction. Transformers consist of two or more coils of wire, called windings, that are electrically isolated but magnetically linked. The primary winding is connected to the source of electrical energy, and the secondary winding is connected to the load. When an alternating current flows through the primary winding, it creates a magnetic field that induces a voltage in the secondary winding. The ratio of the number of turns in the primary winding to the number of turns in the secondary winding determines the voltage transformation ratio. If the secondary winding has fewer turns than the primary winding, the transformer is a step-down transformer and the voltage is reduced. If the secondary winding has more turns than the primary winding, the transformer is a step-up transformer and the voltage is increased. Transformers are used in a wide variety of applications, including power distribution, electronic devices, and industrial equipment. They are essential for transmitting electricity over long distances because they can increase the voltage to reduce current, which minimizes transmission losses. Transformers are also used to step down voltage to safe levels for use in homes and businesses. There are several different types of transformers, including power transformers, distribution transformers, and instrument transformers. Power transformers are used in high-voltage transmission systems, while distribution transformers are used to step down voltage for local distribution. Instrument transformers are used to measure voltage and current in high-voltage circuits. When selecting a transformer, it is important to consider its voltage rating, power rating, and impedance. The voltage rating should match the voltage of the source and the load. The power rating should be sufficient to handle the load. The impedance affects the transformer's ability to regulate voltage and handle fault currents. Regular inspection and maintenance of transformers are essential to ensure their safe and reliable operation. This includes checking for oil leaks, overheating, and damaged components. Over time, the insulation in transformers can degrade, which can lead to failure. Understanding the principles and operation of transformers is crucial for electrical engineers and technicians. Another topic is overcurrent protection. Overcurrent protection is the practice of interrupting the flow of electricity when the current exceeds a safe level. Overcurrents can be caused by short circuits, overloads, or ground faults. Overcurrent protection devices, such as circuit breakers and fuses, are designed to automatically trip or blow when an overcurrent occurs, thereby protecting electrical equipment and preventing fires. Circuit breakers are resettable devices that trip when an overcurrent is detected. They contain a bimetallic strip or an electromagnet that responds to excessive current. When the current exceeds the breaker's rating, the strip bends or the electromagnet trips a switch, interrupting the circuit. Fuses are one-time use devices that contain a fusible link that melts and breaks the circuit when an overcurrent occurs. Fuses are available in a variety of types and sizes to accommodate different applications. The National Electrical Code requires that all electrical circuits be protected by overcurrent protection devices. The size and type of overcurrent protection device should be selected based on the ampacity of the circuit and the type of equipment being protected. When selecting overcurrent protection devices, it is important to consider their interrupting rating. The interrupting rating is the maximum fault current that the device can safely interrupt. The interrupting rating should be greater than the available fault current at the point of installation. Coordination of overcurrent protection devices is also important. Coordination ensures that the overcurrent protection device closest to the fault will trip first, minimizing the impact of the fault. Regular testing and maintenance of overcurrent protection devices are essential to ensure their proper operation. Circuit breakers should be tested periodically to verify that they trip at the correct current level. Fuses should be inspected for damage and replaced if necessary. Understanding the principles and practices of overcurrent protection is crucial for electrical safety. And for wiring methods, various wiring methods are used in electrical installations, each with its own advantages and disadvantages. Some common wiring methods include rigid metal conduit, electrical metallic tubing, flexible metal conduit, non-metallic conduit, armored cable, non-metallic cable, and cable trays. Rigid metal conduit, RMC, is a heavy-walled steel or aluminum conduit that provides excellent physical protection for conductors. It is typically used in harsh environments or where there is a risk of physical damage. Electrical metallic tubing ENT is a lightweight steel conduit that is easier to bend and install than RMC. It is commonly used in commercial and industrial buildings. Flexible metal conduit FMC is a flexible conduit that is used to connect equipment that may vibrate or move. It is also used in tight spaces where it is difficult to install rigid conduit. Non-metallic conduit, such as PVC conduit, is a lightweight and corrosion-resistant conduit that is used in underground and wet locations. Armored cable, also known as BX cable, is a flexible cable that contains conductors wrapped in a metal armor. It is commonly used in residential wiring. Non-metallic cable, such as an M cable or Romex, is a flexible cable that contains conductors wrapped in a non-metallic sheath. It is commonly used in residential wiring. Cable trays are open support systems that are used to support and route cables in industrial and commercial buildings. The National Electrical Code specifies the requirements for each type of wiring method. These requirements include the type of conductors that can be used, the size of the conduit or cable, and the spacing between supports. When selecting a wiring method, it is important to consider the environment, the type of equipment being connected, and the applicable codes and standards. Proper installation of wiring methods is essential for electrical safety. This includes properly supporting the conduit or cable, making secure connections, and protecting the conductors from damage. Regular inspection and maintenance of wiring methods are important to ensure their continued safety and reliability. This includes checking for damage, corrosion, and loose connections.